Hi, welcome. Welcome to the C3 AI DTI seminar series for the full semester. My name is Richard Zhang, and I am an assistant professor at the University of Illinois. I'm co-organizing and co-hosting the semester's seminar series with Gary Joshi, who is an associate professor at CMU. So the C3 AI DTI features research that focuses on studying how artificial intelligence, machine learning, and big data can lead to scientific breakthroughs with large-scale societal benefits. And before we begin, we would like to pause to acknowledge the support from our academic and industry partners, for which we are deeply grateful. So our fall 2022 series is organized around two special themes: adversarial machine learning and distributed and federated learning. Our talks are scheduled to alternate between these two themes over alternating weeks. We're really excited to have some very great speakers lined up for the semester. Just to give you an idea, we'll be hearing from Pingyu Chen from IBM today, and John Ducci from Stanford next week, Nicholas Carlini from Google Brain the week after, Gary Joshi from CMU the week after that. So you can find abstracts for future talks on our website. Videos of previous talks will be posted on our YouTube channel, and we invite you to subscribe to our newsletter and our channel so that you don't miss these talks. So today we're very happy to welcome Dr. Pingyu Chen to share his research with his talk entitled AI Model Inspector Towards Holistic Adversarial Robustness for Deep Learning. Pingyu is a principal research scientist at IBM Thomas J. Watson Research Center in Yorktown Heights, New York. Chen is also the chief scientist of RPI IBM AI Research Collaboration and PI of ongoing MIT IBM Watson AI Lab projects. So Chen received his PhD degree in electrical engineering and computer science from the University of Michigan and Arbor in 2016, and recent research focuses on adversarial machine learning and robustness of neural networks. So without further ado, let's welcome Pingyu. The talk will be 50 minutes long. For the audience, please use the Q&A feature to submit your questions. We will ask them on your behalf at the end of the talk. So whenever you're ready, Pingyu.
Yeah, okay. So yeah, let me do a timer so I don't go over time. Yeah, and yeah, so I would like to start by sharing my screen. Okay, are you able to see the full screen?
Yes, looks great.
Okay, yeah, so thank you again, Richard and Gori, for the invitation. So today I'm going to share my kind of research journey and things I have been doing on adversarial machine learning and my vision in this domain, and summarize them into 3 words that will be AI model inspector. So I know this is like Thursday, noon-ish or afternoon in US. So let me start with something fun, right? So last year our IBM PR and communication person reached out to me and saying, "Oh, you seems to be very active in this space, right? So can you tell me in layman terms what you are doing in this space and how you are helping to build a better AI technology?" So I basically described to them what I'm doing, and then they wrote a very nice article about that. But one kind of embarrassing thing is that they basically made a title of the man who challenges AI every day, without letting me know, right, until I saw the article. But on the second thought, I start to appreciate and agree this title in the sense that this is exactly what I do at IBM, right? Especially I'm in a very unique group of trustworthy AI, where we study different aspects of trustworthiness to improve our AI technology, right? Including robustness, explainability, fairness, privacy, and many others. So through this unique environment and these business opportunities and discussions, I think I would like to provide a very unique view of the development in AI robustness in this field. So my research vision, as I mentioned, I would describe it as a conceptual framework that I call AI model inspector. So ideally, what I would like to convince you today is that we should really sit down and think hard about how we can most leverage machine learning techniques to develop a better tool for us to actively and continuously identify mistakes that could happen in today's AI machine learning systems, and how we can mitigate those risks in an efficient manner. And this inspector should really be be fully operational in the full cycle of the AI model, ranging from training and deployment phases. And I will talk more about that in later slides. But eventually, our view, also shared by many of our colleagues, is to create a trustworthy AI ecosystem, right, that can feature self-correction and quick adaptation to challenges and risks that will emerge on the horizon. So for those of you who have been working on developing AI algorithms and systems for a long time, it shouldn't be a surprise to you that there is a gap between AI development and deployment, right? So an analogy I often want to make is, doing AI development is just like growing plants, right? So normally, as a researcher, we grow our AI technology in a greenhouse, right? Which means we assume the data ID, the models are transparent and there are ideal conditions to train a machine learning model and evaluate it on a well-curated data set. However, when we actually deploy the model in the wild, right, a lot of crazy things could happen, right? There could be, data shifts, right, like, or the discrepancies between training and testing evaluations, or even we will be compromised or being threatened by these bad actors in the wild that try to break our systems. So this motivates, right, why we really need to make AI robust, right, to make sure it is not only useful in the greenhouse, but it can also survive and be deployable in the real world. And one important motivation to motivate this research is from an adversarial perspective, right? So a recent Gartner report actually mentioned, right, that by 2022, which is this year, the more advanced cyber attacks will actually involve data poisoning, model theft, or adversarial examples. So these terms are basically associated with a new type of cyber attacks targeting the fact that more and more enterprises or services are using machine learning as part of their system or their service. So these attacks are emerging to target the machine learning part of the system for the bad actor to gain their leverage. On the other hand, a survey also shows, right, out of the 28 organizations, right, 25 of them actually recognize they didn't know how to properly secure their AI systems against this type of an attack. So on one hand, we are all excited about the AI revolution to come, but on the other hand, there's no denial that these bad actors could also leverage these advanced AI techniques to do bad things, right? And examples were already being shown, like deepfakes and a lot of these prototype attacks that have been being discovered. Okay, so why do we care so much about adversarial robustness, right? So adversarial robustness in a formal sense is we want to understand the model performance in the worst case scenario. So this is different from the typical approach to evaluate model performance, right? Typically, we evaluate model performance like accuracy in the average sense, right? Like, for example, reporting the test accuracy on the test set. But in adversarial robustness, we really care about how your model will survive or how your model will perform in a worst case scenario, right? Where worst case, right, can be defined by some actions that the attackers are allowed to do or take to make a change to your system or to your data. So in a high level, right, all of this study, right, is trying to prevent possible prediction evasive manipulation on our machine learning systems. And there are several reasons we want to do that, right? So from the perspective of users, right? So whenever users see these failure cases of AI, right, they will be scared of this technology and intended not to use this technology, right? So examples are like there are prototype attacks showing, right, you can add some stickers on the roads, and some autopilot driving systems, right, will force the car to drive in the wrong lane and possibly cause some car accidents. And there are also some well-known examples that you will add some stickers to some stop sign, and for some unknown reason, the autonomous driving system will think this is a speed limit rather than a stop sign, so the car wouldn't stop in front of the stop sign. And we also recently demonstrated that we can design some adversarial t-shirt with some special design pattern that will basically make whoever people is wearing that will be invisible to a person detector. And as a model developer, right, you will be very surprised to know, right, like why my model already gets 99% accuracy on the test set, but still my model is so vulnerable to these adversarial attacks, right? That means there could be some fundamental limitations in our current practice of training machine learning models. So as a model developer, we always want to be more proactive and actively evaluate possible negative impacts that could happen by using our machine learning model, especially for some high stakes decision-making tasks. And finally, as a model owner or a business owner, stakeholder, you will really want to make sure the services that you provide is safe and responsible. Otherwise, it will bring negative impacts to your revenue and reputation. So we have seen some cases like some company put a free-to-use chatbot, right, to intentionally to do good for the society, but very soon, without careful monitoring of the behavior of the agent, right, the agent was soon taught by these bad actors to be a racist or being a very biased agent, and it end up needs to be taken down because it's misbehaving in this platform. Okay, so with all these motivations in mind, now I'm going to formally introduce adversarial robustness with the introduction of the life cycle for AI. So I will divide this AI life cycle into two phases. The first phase is training, and the second phase is the deployment. So in the training phase, it typically includes how we collect data and how we process data. And the second stage in the training phase will be how do we select model to train on the data we collected, right? So the model can be a standard machine learning model like a decision tree or a gradient boosted tree, or it could be a deep neural network, depending how you want to use your technology for. And once your model is fully trained and tuned, we will deploy the model. And there are also different modes of deployment. So if you are deploying your model through a service, right, like an API, then your model is more or less a black box to a user, right? Because as a user, I can use the function provided by the API, but I will never know what that model is, right? It could be a decision tree, it could be a neural network. The user never know. On the other hand, there would be another mode of transparent deployment. In this case, all the model architectures and weights will be available to the user, right? So one typical example is Hugging Face, where they provide all the checkpoints of the transformer models on their repository for users to use. So based on this life cycle perspective, now we can define what attackers can do. And depending on what the assumptions of the attackers can do in this space, there will be correspondingly different attacks that can be discussed and considered in this domain. So for example, if you assume the attacker can have access to your training data and have the ability to modify parts of your training data, then we are basically talking about training phase attack. And there are typical examples like a poisoning attack that try to add some data to your data point, to your training data to such that the model will fail to generalize in the test time. There are also some backdoor attack that the attacker injects some triggers to the training data and try to manipulate the output of the machine learning model after it is trained on this poison data. And I will make an example in later slide. And for adversarial example, it's basically an evasion attack. In this case, we do not assume that the attacker has the ability to access the training data, but we do assume the attacker can make some observations of the model at the deployment phase, either a white box or a black box setting. And they can iteratively use the knowledge to generate an adversarial evasive predictions. Of course, this view of adversarial robustness also includes more classical security issues that could be accompanied by deep learning technology, like extraction attack, like how model inference, data privacy, and so on. And overall, this adversarial robustness can also be extended to include more recent discussion in terms of AI value alignment and AI governance and so on. But for this talk, I'm going to highlight the first three rows that are check marks that are basically attacks or targeting on the machine learning algorithms itself. Okay, so recording these three states, right? Like these two phases I have for the AI lifecycle. So we can already introduce this robustness inspection in the context of this AI lifecycle. So between the stage of data collection and model training, right? So what we can do to ensure robustness and do robustness inspection is to do some data sanitization. For example, look at the data you have and try to remove some spurious or problematic data samples. And between model training and model deployment, we should really make sure we are doing a complete and comprehensive performance validation to make sure the model can be deployed safely and responsibly. And if after the model deployment, we discover some issues at the wrong time, then we should really think about how do we continuously monitor the behavior of the model being deployed. And if necessary, we should take down our model and recollect data and retrain the model to make sure the model can be deployed and used in a safe way. So on the right, I'm basically highlighting some major challenges that have been considered in our community, both in the model development and model deployment phases. So model development phases, we talk about those training time threat models that I just described. And for model deployment phases, right, we care about the model performance in the worst case, right? In this case, the robustness to adversarial examples. And more recently, we also expand the scope to consider the model performance in terms of out of distribution generalization, right? So these are not necessarily the adversarial, the most worst case scenarios, but this could be related to some natural scenarios where your data have undergo some domain shifts, and you still want to make sure your model can be robust to these natural occurring shifts happening in the real life. Okay, so with these threat models and these robustness challenges in mind, now we can talk about what can be a nice framework to really detect and fix those issues that we identify for AI robustness. And that's why I call it AI model inspector. And more generally, it also relates to the concept of AI maintenance. And we have a paper that's going to be published very soon at IEEE Computer to talk about this concept. So the idea, I would like to make analogy to some cases that is more familiar to the audiences. That will be the car maintenance, right? So when we are using our cars, right, it's very natural that we take our car back to the inspection and maintenance shops, right, to make sure there's nothing wrong with our car, right? And if something is happening and going wrong with our car, we will ask the maintainer to fix our car. So we would argue that we should actually do exactly the same thing for our AI technology, right? So we start by taking the model that we are going to deploy, and we run our model by a checklist to benchmark the performance of this model in terms of different dimensions of robustness, right? And we can, in the first stage, we will first run some detectors, right, or some scanning tools to make sure to identify are there any possible robustness issues hidden in the model provided. And once any robustness issues it has been identified, right, the second stage will be how do we mitigate those issues that we identified. So detection and mitigation, these two stages basically constitute the AI model inspector framework. And finally, right, after these detection and mitigation stages, right, we will return a nice and clean and robust model to the user for safe use. So I also wrote an article, right, try to articulate this point, right, like cars require regular inspection. Why should AI models be any different? Just to familiarize the practitioners with this concept. Okay. So how do we achieve a holistic adversarial robustness, right? So I talk about different dimensions of possible weaknesses and threat models. So what is the holistic picture of this adversarial robustness, and how do we get there? So based on my industrial experiences, right? So the ideal solution, right, to achieve holistic adversarial robustness really has these three key components. The first idea will be model agnostic. So we would hope an ideal solution to be agnostic to a particular model you are using, right? So that solution has to be generalizable across different machine learning models and architectures and so on. But on the other hand, it should also try to maximally leverage the domain knowledge it has, right, to improve robustness, right? So for example, there are some physical rules or some grammars or some language rules that we can leverage to help us improve robustness of the models we are deploying. And the third dimension, which I would argue is a very important but often overlooked dimension, is the practicality. So most of the time, we are trying too hard to make our model robust, but we compromise too much the utility of the model, right? So as an industrial practitioner, right, if we are providing a solution to make the client's model robust by sacrificing like even 5% of the accuracy of the original model, then that will not be a viable solution because that will reduce the utility too much. If you are a software engineer, right, you would like to do some penetration testing of the AI technology we are deploying as well. So throughout the different life cycles of the AI model, you would hope that we do sufficient testing and evaluation of the system we are developing and deploying to make sure it is in a stable stage. So with this holistic adversarial robustness in mind, I would like to map the terminologies being used in this domain to some general and common terms that a regular or broader audience will care about, right? So most of the time when we are talking about attack, right, actually we mean finding bugs in the AI systems that we are developing, right? So this means we are doing a lot of in-house sensitivity and reliability tests before that model is actually being deployed. And most of the time, we would like to see, given some constraints, right, some possible search spaces, are we able to find some counterexamples that violates the design of our model, right? So this is in a way very similar to debugging. And whenever we are talking about defenses, right, we are really talking about model hardening, right? So how can we detect and mitigate the risks that we found? And this mitigation strategy has to be practical, right? The best case is it is a plug and play defense that you can apply on the fly to any model, right? Instead of asking to retrain the model. And the third area is called verification, which is actually relates to model certificates, right? So in some particular domains, we would like to provide some attack-proof guarantees of the model we are using, right? Especially like applications requiring high reliability, like autonomous control systems, for example. So in those domains, whenever you are using a machine learning technology, you would be required to certify the capability of your service that you are going to use. So this is really relates to AI governance and AI standards and law regulation. And the final dimension is the applications to AI. So through understanding the vulnerability and weaknesses of the AI systems, especially deep learning models, we can actually twist the lessons, right, to do some new applications to AI. And I will show two examples in this talk, how basically those are applications inspired by studying the adversarial robustness of neural networks. Okay, so in the remaining of my talk, I will show 5 research highlights following this holistic view, and these are 4 different pillars of holistic adversarial robustness. So the first research highlight I want to make is finding failure modes of the AI systems we are using. So although our final goal is to improve and make sure our AI model is robust, but the first step is always to show the current AI model and service is not robust, right, or it possibly can fail. So this means over the years we have put a lot of efforts, right, to design and implement a lot of practical robustness testing tools to show to evaluate the empirical robustness of different data modalities and different machine learning models developed over time. And this finding failure modes, right, also depending on whether the model under testing is a white box model or a black box model. And this testing also spans from both digital space and physical space. So this is one example of a physical adversarial T-shirt that I just mentioned. Let me play it. I think I can play the video. Okay, so you can see in most of the frames, right, the person wearing the T-shirt will evade the detection of the person detector, basically the bounding box will disappear because of the bounding box is being misguided by the pattern that we designed. And on the right, we are showing these adversarial images for captioning tasks. So on the top, we are showing the original image, right? So if you look at the captions generated from this image, it will say a red stop sign sitting on the side of a road, which I would argue is very precise and seems to know everything correct about the content. However, when we add a very small amount of noise that is basically unnoticeable to human to the same image, and this is what we call an adversarial example. In this case, right, the output of this image from a state-of-the-art captioning system, right, will actually say a brown teddy bear lying on top of a bed. But obviously, we do not see any brown teddy bear, and also not a bed, right, in this image. So these examples, right, really challenge what machines know and what technology, right, what features the machines are using to make the prediction. And it's even questioning whether those predictions are robust and precise or not. So the last example I want to show for this highlights, right, is this example of finding adversarial examples to evade the detection of fake news. So we are showing here is the black text is the original paragraph, right? So the original paragraph will be classified as a 100% fake paragraph. But if we do some paraphrasing of this paragraph, right, by preserving the semantic meaning of the same paragraph, right, by changing man to guy and drive through with the correct spelling and so on, right? So with these very minimum changes, the modified paragraph, right, will actually be predicted as a 77% real instead of a fake one, right? So this already shows how attackers, right, can leverage this technology to design better text that evade the detection of a fake news detector. So I would like to give a spotlight on this zoo attack that we proposed. This is actually also my first work in this space. So at that time, when we look at the literature, right? So adversarial examples can be generated, but they are only they are only often studied in a white box setting, which means that the model is transparent to the attacker. And we are scratching our head and asking, is that a practical scenario, right? So what happens if the attacker only knows some knowledge of the model the attacker is attacking, right? Like the black box setting. So in this case, you can think about it as a black box optimization problem in the sense that we are given an image, and the attacker's objective is to find some perturbation to the bagel image such that the perturbed image will give a different prediction, provided that the range of perturbation is pretty small, right? Like we confining the maximum allowable perturbation to every pixel values, for example. So this will be a black box setting. So how do we do these things in the black box setting, right? So we already know in a white box setting, finding this perturbation is actually very straightforward, right? So in a white box setting, we can simply just use backpropagation provided by a deep learning model, right? By asking if I want to add a perturbation to make a bagel being classified as a grand piano, right? So what is the gradient of that objective function? And then we can basically add design a perturbation based on the gradient as a guidance. But in the black box function, since this is a black box, so obtaining gradients is impossible. So in this case, what we are proposing back in 2017 is to estimate a gradient, right? So we can estimate a gradient of every pixel value for the perturbation, right? As simple as some calculus, right? How we do slope computation, right? By perturbing plus and minus beta in the function value and divided by 2 beta to obtain the estimated slope at that particular dimension. And then we can follow a gradient descent steps using these estimated gradients, which is actually called the zeroth order gradient descent, because we are only using zeroth order, basically the function values to figure out the gradients. And then we are using gradient-like the algorithms to find these adversarial examples. So this attack turns out to be very successful, especially in a black box setting. And it also indicates, right, hiding the information of your model would not make your model more robust. And more interestingly, it actually has a more practicality than you can imagine, right? So for example, this solution is actually being quickly adopted in many of the IBM Watson products, right? Because we can wrap anything as a black box function, and it will remove any dependency from the backbone of the deep learning model, right? So no matter it's a TensorFlow or PyTorch or even a scikit-learn, right? All we need to do is to wrap that model as a black box function, and then we can apply the same evaluation protocol to generate black box adversarial examples. So this is very favorable to these enterprise level solutions. And we also shift the focus of black box attack from transfer attack to query-based attack. So prior to our work, black box attack is often done by generating adversarial examples from a white box and another white box model, and then you hope the adversarial example generated from that model will transfer well to the target model that you are actually attacking. So you can already sense some loss of performance for during transformation, during transfer, right? When you are doing this transfer attack. However, for a query-based approach, this black box attack is directly attacking the target model itself. So it will usually give you a better and more precise empirical robustness in the black box setting. And because of this use case, right, it actually also inspired many follow-up works on how do we further improve the query efficiency and generate more powerful black box attacks for robustness testing. And also, it also being added as a new application in many of those zeroth order optimization literatures. We even take this idea further, right, by consider some new applications based on this idea. So we can also leverage this idea of generating adversarial examples to generate contrastive explanations for machine interpretation. So I would like to make an example, right? So imagine you have multiple friends, right, who have the same name called Steve. And so how do you identify a particular Steve? You will say, oh, I'm talking about the Steve who is a tall guy with long hair, but who does not wear glasses, right? So the feature of not wearing glasses, right, although the glass is absent, it's actually very important to explain which Steve you are talking about. So we try to make an example of this explanation to the machine learning model, right? So for example, if a handwritten digit classifier says this digit is the 3, right? A user will be asking, oh, can you tell me why you think this is a 3? So using these perturbation ideas, right, we can generate 2 sets of images, right? So this image will identify a sufficient part, minimally sufficient part of the input that will support the decision of 3, right? So you can see this cyan highlighted part kind of shows the structure of 3. And also the algorithm will also show some parts that is necessarily missing to prevent the model from making a different prediction, right? So for example, if this purple bar is added to the data input, it will be classified as a 5 instead of a 3. So the final explanation will be this image will be classified as a 3 because the cyan parts are present, and also because the purple part is missing. So we are arguing this explanation is more intuitive to human than these commonly used correlation-based studies. Another example from this black box optimization will be molecule optimization. So in this case, we are interested in finding a better molecule starting from a lead molecule, like some solutions or some in the drug design process where we already have some solutions, but they are not ideal, right? So for example, some properties are not met, right? So we would like to start from that structure and modify the structure a little bit to improve the property, like lower toxicity, better salutability, and so on. So in this case, we can design the whole search process as an end-to-end black box optimization program, where we first start with a lead sequence and encode that sequence into some continuous latent space, and then decode it again, and then pass that decoded sequence to several black box property predictors to predict the properties. And we can set the threshold like, oh, I want the optimized molecule to have a salutability greater than a certain value and toxicity lower than a certain value, and so on. But the entire process can be modeled as an end-to-end black box optimization process by searching through the latent space with the guidance from the property predictors. And this paper is actually published at the Nature Machine Intelligence this year. And so we have some, we basically can use this idea to design very efficient search process and for optimizing molecules with design constraints. So this is the first research highlight. The second research highlight I would like to present is actually the trade-off between accuracy and adversarial robustness. And this is what actually motivates us to look deeper in this space, right? So one experiment that we did back in 2018, which is kind of well known in this domain, is we take 18 different imaging models published over time, right? And then we rank their performance as the top one accuracy on the x-axis, which is how typically people benchmark the performance on ImageNet. What's interesting is we also ranked their performance in terms of how sensitive they are to input perturbations, right? So the smaller the y value is, right, the easier the model can be perturbed by these adversarial examples. So what is very kind of unexpected to see is models who are actually more accurate. At the same time, they are also more sensitive to these input perturbations. So this basically shows if we are still using the standard accuracy as the only metric to evaluate and rank the model performance, right? We may miss the big picture, and we are actually not making the right progress if you want your model to be robust and accurate at the same time. But however, this figure does not mean this trade-off cannot be eliminated, right? So over the years, people have been developing new methods, right, like adversarial training or different types of training methods try to mitigate this trade-off. But what I'm trying to show is that the accuracy itself, right, only provides very limited evaluation of the actual performance, especially if you care about your model to be robust, right, not just being accurate. So we also take this quest and expand the scope of evaluation to a broader range of robustness, like I mentioned in the earlier slides, right? So in addition to adversarial examples, we can also evaluate the robustness of a given model under different scenarios, right? So for example, researchers have developed a lot of evaluation data sets, right? For example, images under common corruptions, distribution shifts, semantic changes, and so on. So with all those data sets, right, we are able to collect a suite of those benchmark data sets. And whenever a model is being developed, in addition to the standard accuracy, we should also benchmark the model's performance on those diverse data sets, representing different robustness in different aspects. So one work that we do recently is we evaluate region transformers robustness using this principle, right? So region transformers is something that is very popular nowadays by modifying the transformers, which is already designed for a natural language processing task, right? By adding some small changes to the transformer, and it shows a good performance on computer vision tasks, and which basically means, transformer has the potential to become the foundation of the multimodal machine learning scenarios by using the same architecture to handle different modalities. So we have done a lot of evaluation in this paper, and we actually show in most cases, vision transformers are indeed more robust than state-of-the-art convolutional neural network, like a big transfer. And there are also, we do a lot of reasoning on where the source of robustness comes from, right? So for example, a smoother input loss landscape can be observed comparing between vision transformer and bit transfer. And if you are interested in knowing more, we are actually giving a tutorial at the New Rips in this December, talking about how do we evaluate foundational robustness for foundation models. So we can also do the same study, right? So whenever new architectures emerge, right, we can always include them to have a complete analysis in terms of their accuracy and robustness. So this is a plot comparing different available checkpoints related to pure convolutional neural networks versus pure transformer neural networks, and also a hybrid version, which is a combination of convolution and transformer architectures. So something interesting to observe is that transformers overall seems to be better if you care about making your model accurate and robust. So most of the transformers are on the right top corner of this figure. On the other hand, we also observed that some more recent convolutional neural networks that was inspired by the design of transformers, right, like MLP mixers, it actually can improve the robustness, right, by being more like a transformer and then being less like convolutional neural networks. So this plot basically shows, if we care about making our model robust and accurate, right, then the choice of architecture really matters. Okay, so the third highlight I want to make is after talking about attack and evaluation, now we are moving to detection and mitigation of the risks that we identified. So there are several things I would like to mention, like how do we make this defense practical, right? So first of all, we would like to hope there will be some plug and play techniques that can quickly identify risks and quickly fix those issues without retraining or redoing everything from scratch. So it's really about data and resource efficiency to make the defense practical. So I would like to make an example based on backdoor attack, right? So backdoor attack, if you recall, it's a training phase attack that basically attackers can inject some poisoned images. In this case, some portion of the training data has been appended with this white square as a trigger pattern. And all the images associated with this appended image will be mislabeled as a 4 instead of the actual digit class. So whatever deep learning model trained on this poison data set, right, will be a backdoor model. So which means whenever the trigger is present in the data input, because of the memorization effect, the model will say it's a digit 4 regardless of the content. On the other hand, without this trigger, right, the model will behave just like a regular model and making correct predictions. And that's why it is called a backdoor attack, because the attacker can gain control over your output as long as the backdoor, in this case, the trigger is being placed at the data input. And this backdoor attack can actually be amplified, or it becomes an even bigger threat, right, to federated systems, right? And this, I know this is also an important topic in this seminar, right? So in this case, right, there are multiple clients holding private local data, and they want to jointly train a federated model with limited sharing of the data they hold at their own hands. So in this case, if you think about the case that some bad actor has some control over a small set of the agents in the process of federated learning. And so in that case, the bad actor, right, can distribute the backdoor pattern into several pieces, right, and basically better hide the trigger of the backdoor pattern. And in that case, we can actually show that this distributed attack is actually more prominent in federated learning compared to centralized setting. And even if you employ some robust federated learning protocols, you are not able to effectively eliminate or detect these distributed backdoor attacks because of this additional privacy constraint imposed on these distributed and federated learning scenarios. So how do we detect and mitigate these threats, right? So, and to those of you pondering why this is a question, right, or a concern, right, I would like to motivate with this example, right? So, but if I tell you I have an amazing ImageNet model, right, who has a 95% accuracy, right, do you want to use it for your own task, right? So your first instinct will probably be yes, right? Why not, right? This is the best ImageNet accuracy, best ImageNet model I have ever seen so far. Right, but if you are thinking about from a security and robustness perspective, right? So if this model is not well certified, or is actually being provided by some unknown, untrusted third party, right? So you would be concerned, right? Are there any backdoors being hidden in the checkpoints or not? So you would so as a user, right, or to make sure responsible use of your technology, you would like to hope that we have some way to certify or to sanitize the model before using it. So in this case, right, so we can practice our AI model inspector, right, by first detect possible backdoors in the model, right? So we are again given a model, pre-trained model weights, and we will going to run some tests to detect whether this model has backdoor or not. So one example is using the paper that we published at the ECCV at 2020. that we actually compare the perturbations of a set of images, right, between their universal perturbation versus individual perturbations. And if their activities are alike, that basically means there could be some backdoor pattern hidden in the model. And if not, that basically means this model is a backdoor free. So we have a detector in place that can detect whether a model has backdoor or not. So upon detecting a model has backdoor, the next stage, right, will be mitigation, right? So how can you wash away the backdoor effect in those models? So in another paper, we basically provide a solution by looking into the loss landscape of the models, right? So, starting from two poisonous and backdoored models in the loss landscape space. If you follow this mode connectivity property of neural networks, which basically means there is a path of low loss connecting two different local minima in the loss landscape. Then as long as we can use our available data to find that magical path, and we can basically choose a model that is away from those two poisonous models, then ideally this model will still retain high accuracy compared to the given model. But still, because the model is far away from that starting point, then ideally the model would not have any backdoor effect, right, compared to the original problematic model. So this is how we propose that use this mode connectivity for deep learning to return a clean model to the user and still retain high accuracy. Okay, so the fourth research highlight I want to make is related to verification. How can we provide provable robustness assessment and quantification? So as I mentioned, this is very important for applications that require rigorous justification about the level of violation for the machine learning model to be deployed. So ideally we would like to have a way to a score, right, to quantify the level of robustness, right, especially when we are doing some defenses or some mitigation strategies on a given model. We would like to have an independent score to show, to quantify how much of the improvement our model may have to the changes we made. And the other motivation is like for verification, right? So given one model, right, can we quantify, like, and also given a thread model, right? So for example, allowing the image to rotate within a certain degree, right? Can you certify no matter how I rotate this image, right, the output of the model will always be consistent? So geometrically, right, we can understand this verification problem as a perturbation or a margin based analysis, right? So this ostrich image that we have, right, can be seen as a data point in the high dimensional space, right? The representations learned by the neural network. And these dashed lines are basically the decision boundaries provided by the neural network. So in this case, adversarial example will basically be some point nearby the given sample, right? But they are very close, so they will look alike. But on the other hand, this adversarial example lies on the other side of the decision region, so it will be classified as a shoe shop, not an ostrich label. So certified robustness or neural network verification basically means, are you able to quantify a safe region, right? This, for example, this green region that we have, such that no matter how you perturb your model, your data sample, as long as the perturbed sample still lies in this green region, then we can guarantee the model's top one prediction will not change, because the perturbed sample is still lies within the same classification region. So verification problems in a way try to certify the region, right, that can guarantee consistent prediction of the model. And you can generalize this idea to different perturbations, right, like semantic perturbations or pixel value perturbations and so on. So one typical way to do this verification will be do some bound propagation, right? So starting by assuming you are allowing the perturbations, some level of perturbation in the input space, then you will propagate this the perturbation effect layer by layer and doing some necessary linearization of the perturbation effect and propagate that to the output of the neural network model, right? So one way to check whether your model is robust to these epsilon perturbations, right, will be asking the lower bound of the model output, right, for the ostrich class, right, is a greater than any upper bound of all the other classes. If that's the case, then you can certify for this sample, the model is epsilon robust, which means no attack can change the label of the perturbed sample as long as the perturbation is within this epsilon range that I certified. We also did some demo to show this verification in evaluation score, right, actually can be well mapped to humans' perception of choosing the robust models. Okay, so in the interest of time, I will probably skip the final highlight I want to make, but I want to jump to the page that I think can give you a high-level idea of why I'm so excited about this technology. So this is the final pillar that I want to cover, which is called model reprogramming. So I would describe it as a new way to do data efficient transfer learning, right? So typically people do transfer learning by take the target domain data and fine-tune some subset of the parameters in the pre-trained model. But model reprogramming tries to do something different and actually tries to do something across domains by, instead of changing the model weights, right, we keep the model weight as is, and then we attach 2 layers before and after the pre-trained model from a given domain. And this is particularly interesting, right, if we can to leverage the pre-trained models available in some domains and to tackle the machine learning problems in some data limited domains. So over the years, we have shown this technique can be very useful, right, to do some cross-domain learning. For example, reprogramming speech models to do time series classification and reprogramming language models to do molecule learning problems, or reprogramming computer vision models to do biomedical measurements. Where the source domain is open data rich and have a lot of available pre-trained models. On the other hand, the target domain, right, is often resource limited in terms of the number of available data, and there's usually do not exist good pre-trained models. And we also argue that model reprogramming could be a more efficient way to leverage large pre-trained models, like as large as the foundation models, right? How can we leverage those pre-trained models and really to enable cross-domain resource efficient learning. And recently I've wrote a survey paper on this topic, and all this model reprogramming idea is actually inspired and motivated by studying how we can manipulate the decision makings of the model. So it's more like adversarial machine learning for good in my point of view. Okay, so over the years, I think we have made a lot of visibility in this space, and I would argue that adversarial robustness is one of the very few areas that has caught attention not only to academia, industry, and also to general users, right? So users like to know like how robust our models we are, how robust how secure the AI technology that we are offering, and what are the consequences, right, when they fail, right? So over the years, we published several papers and do tutorials and also release open source libraries to encourage the community to work together, right, to improve the robustness at the fastest speed as we can, right, to make sure our AI models are not only accurate but also robust and safe to use. And this, for example, this adversarial robustness toolbox is some open source libraries developed by IBM and recently donated to Linux Foundation AI for greater use. And it is also actively being used by some DARPA program to evaluate the defenses submitted by different teams and sometimes in other programs as well. Okay, so to wrap things up, I would like to offer some takeaways. So first of all, I would hope that through my talk, you will now be convinced that adversarial robustness is a new and very important AI standard if we want to make our machine learning technology trustworthy. But however, most of the time, robustness does not come for free, right? So we show those failure cases in both digital and physical world and across data modalities and machine learning models. And the most important lesson is, don't trust your standard accuracy too much, right? So higher accuracy usually do not mean better robustness by default. And also we need to be proactive in the sense that there will be bad actors, right, in the wild that also tries to leverage this advanced machine learning technology to make their own benefits. So to have a holistic view of this AI robustness and adversarial machine learning, right, I propose we look into this AI model inspector framework, right, to provide a holistic understanding and evaluation of the machine learning technology we are using. That includes these 4 different pillars that I talk about and the research highlights, right, like finding bugs, model hardening, model certificates, and boosting AI model in terms of finding new applications. So, of course, my long-term goal would like to make sure that our AI technology is evolving and being developed in the correct path, and making sure they can be standardized and as reliable and easy to use as a car models, especially from the maintenance perspective. So with that, I will end my talk and open the floor for questions.
Thank you very much, Pingyu, for a very interesting presentation. So to the audience, please type your questions into the Q&A, and while we're waiting for questions to arrive, let me ask a quick question. So Pingyu, you talk a lot about the fact that accuracy and robustness are kind of, right, high accuracy is not necessarily robust and vice versa. Can you comment on the trade-off between the two, right? Like how much accuracy you stand to lose by gaining robustness?
Yeah, sure. So maybe I can go back to the ImageNet example. So empirically, that's what we observe for different ImageNet models, right? So normally ImageNet competition, they only care about the top 1 prediction. So whenever you get a higher top 1 prediction, you are the best ImageNet model according to the competition criterion. But I don't have that here, but in terms of the actual robustness, maybe this one is more precise, right? So even if your standard accuracy is as high as 84%, right, which is like one of the highest you can get in ImageNet nowadays. If you look at the robust accuracy, which means the model correctness under some attack called auto attack, which is a state-of-the-art adversarial attack, you only get 30% accuracy when under some small amount of perturbation on CFAR 10. Also, sorry, this is ImageNet, so it could be like some other perturbations. But these are basically how robust you are against some small perturbations in the input space. So if you care about robustness, you will say there's a bigger gap, right? On the standard accuracy is already 80 something, but on robustness is only 30, right? So there's a big gap that needs to be filled in. And over the years, people are trying to be proposing different technology like adversarial training and so on, try to reduce the gap.
Okay, we have a question from Michael McCoy. Can you expand on how model reprogramming is similar to adversarial perturbations with defense?
Yes. So I didn't take the time to talk about that, but thank you for the question. So the motivation I have is that I have a high-level view of this model reprogramming as some input transformation function, right? So actually, we realize this input transformation function as a universal perturbation to the downstream task, right? So in this case, if our goal is to reprogram an ImageNet model to do this biomedical classification task, all we need to do is to add some perturbation to the target domain, right? And that's effectively what it is doing, is actually to align the representations of the target data to the source representations through this perturbation, right? So ideally, right, if you think about this, right, so if we have a perfect model to classify dog versus cat, and whenever a new target domain comes in, right, so as long as you can map the one class of the target domain to the dog representation and the other class to the cat representation, then we can already reuse the original classification rule to classify the target domain task, right, by treating them as a cat versus dog. So the purpose of introducing this adversarial perturbation is to introduce in a way you perturb your target domain representations in a way that can be recognizable by the source model. And of course, to align the output, you need to do some label mapping between the source label and target label. And that's what the second inserted module is doing.
Okay, so we're actually at time, but we still have a couple questions. Could you stay a little longer? And
yeah, sure.
Yeah, so we have 2 questions from Custom Day, who asks what forms of attack are most worrisome, common for industry, and as an ML grad student, what part of the IBM AI explainability toolkit should they look at first? Which part is the most exciting, usable by third parties?
Yeah, so these are great questions. So I think if you ask different industrial sectors, they will have different answers, right? So there is a survey paper that I pointed out earlier on, like the survey across 28 different organizations. So they actually also surveyed them in terms of what adversarial threat model do you care about the most. And I think the top pick one is actually data poisoning attack, right? Which may be a problem if you are a like AI startup who actively using open data collected from the open domain, right? Like Wikipedia, like the Google Images, right? To do your training. But that may not be a problem if you are doing your machine learning in a closed domain, right? Like financial sectors or some domains where they have a very high confidence about the quality of the data they have. So in those cases, they probably have more concern about the reliability and robustness of their model rather than it's a training time attack. So I would say the answer varies depending on what applications and the industrial use cases. And thanks for bringing up this AI explainability toolbox. So I think now for new graduates, right, young researchers, I think this is a very exciting moment. On one hand, we see a blooming of AI technology and in the open science fashion, right? So nowadays they will not only show the improvement, they will actually also provide the model to that the community to play around. So I think this is a great opportunity that we also try to answer study the trustworthiness of those models, right? So one typical example is this foundation model, right? So as the model size becomes larger and the data size becomes larger, what are the aspects of robustness and other trustworthy dimensions like fairness and explainability, right? Are they becoming even more trustworthy or less trustworthy, right? So those are new research questions that we can address, right? Along with this development of AI technology.
Okay, great. Thank you very much. So thanks again to our attendees and thanks very much to our speaker. Thank you.